So where were we? Swastikas under the beard. Always going to start every class off with an out of context sentence.
And then the following sentence was, that was awesome, was it not?
It was. That was awesome. Well, I mean, at least the guy had seen the error of his ways and decided to grow a beard out to no longer be a hater until his friends. So what does this guy have to like hide now until it grows back out? That or get a new face. One of the two. All right, homework assignment. We had to write methods for our various gates, correct? Our logic gates. Is that it? Class is over. All right, what class is this? 325.
What was that out there?
Oh, I think it was just an empty box that, yeah, it was Professor Wall. It was an empty box that looked like potentially a iMac came in it. But I'll get a notification as soon as it's delivered.
Sorry, guys.
Comes halfway through class. Back up. There we go.
All right, so let's just create a new class here. Let's call this logic. All right, we were supposed to write some methods. And let's make all these, let's make them class methods. Just for, you know, we think about having this little tool and it'd be like logic.and, logic.or, that kind of stuff. So we're going to have a static, let's do and first. So and's going to take in 2 inputs and spit out 1 output. Okay, and just to keep things simple, we'll just do these as ints. No harm, no foul, even though we're only taking in 0s and 1s. All right, so static, int, and int A, int B. Okay, now this guy should return true if A and B are both 1 and false otherwise. So return A equal 1 and B equal 1. That's going to want these in parentheses.
You're having it return an int.
Oh, I am. Actually, we want this return a Boolean, don't we?
Yeah.
There we go.
You could just do.
So we can have it return a Boolean true or false, or we can have it return an int 0 or 1 and then map this to that. This is good enough. So takes in 2 integers, returns a Boolean. If the first integer is a 1 and the second integer is a 1, the whole thing will be a 1, a true. Then we have a static Boolean or int A, int B. This one should return if one of them is 1 or the other one is 1 or both is 1. Or both are 1. That's our or. No, I don't. See, already had it there. How was I missing it, actually? I just didn't copy enough?
Yeah.
All right, so we got ands and ors. What else do we supposed to write? A zor? Takes 2 integers. A zor returns true if exactly one of them is a 1. Make sense? Okay. So this one becomes a little bit more complicated. It should return false under what condition? They're both 0s, or if just one of them's a 0. So let's look at the situations where it should return true. It should return true when A is a 1 and B is a 0. Or A is a 0 and B is a 1. Those are the two conditions in which it should return true. So if this is true or this is true, return true. Under all other circumstances, return false. That look right? All right. So that's a XOR. What else are we supposed to write? XOR. XOR. Okay, so we need a NAND. So NAND is not AND AB. So we can write that in terms of our AND. That make sense? NOR. It's not OR. Then NEXOR. Oh, just a not. Thank you. Here, let's write the not at the very top here. We want not to return a Boolean, or do we want not to return an int? I think we want it to return an int, because we're probably going to use not as part of the inputs to other things. And we'll do a little inline I showed you guys this syntax before. Some of the 250 people maybe haven't seen it. So this is an inline if statement. So this is the same thing as saying if A is equal to 0, return 1, else return 0. So this is the Boolean expression. This separates the Boolean expression from our true value and our false value. Just inline if statement kind of makes things like this easy. But writing the if-else thing like this is just as acceptable.
Just more byte code.
Yeah. And plus, this isn't, I would say many people who only learn Java likely probably have never seen this syntax. So I guess it really just depends on how awesome your teacher is. This is stuff that was really used years and years ago. So just out of curiosity, like for instance, you've had a lot of development. Had you seen this syntax before you met me? You've seen this before? But you've done quite a bit in C and C++?
Yeah.
That's where you've seen it.
Mostly C.
Yeah. Older languages is where this stuff really came from. But it was, since Java is based on C++, which is based on C, it kind of spilled through. So interesting little trick for certain circumstances. But if you're ever writing code, I don't know that I would, if you're writing code that somebody else might need to look at, it might not be real common that people are going to understand the syntax. Kind of a helpful thing. So you'll be the rare few.
Looks smart.
Yeah, I guess. But this was certainly common in older programming. Okay, so that's our not. So if we passed in a 0, it becomes a 1. If we passed in a 1, it becomes a 0. Actually, this one returns a, if we pass in a 0, it returns a 1. If we pass in anything other than a 0, it returns a 0. All right, so we have NAND, NOR, NUXOR. That's our next one. Is that all of them? Okay, so homework assignment was to initially create all of these logic gates in code, if you will, and then do the truth tables for each of them, correct? For all of our different inputs. So we'll just write it. We'll write it inside of logic. So I'm going to have a static int array let's see, I want to have my various inputs. We'll do it this way. Make us look smart. Static string inputs is equal to 0, 0, colon, 0, 1, colon, 1, 0, colon, 1, 1. So those are our various inputs for our truth table. 0, 0, 0, 1, 1, 0, 1, 1. Okay, so here we'll call this inputs. Then we're going to have a static void and truth. Actually, let's just do this. Display truths rather than having a method for each one. All right, so to start off with, we want to go ahead and split up our guys here, our string. So we're going to have a string array split on the colons, which will give us all of our parts. Okay, so we'll split this up on the colon. Then, for each of those parts, which is going to be a string, we want to split that on the comma to get us the first and the second input. That make sense? So we're going to leave it like this, and let's do system.out.println and truth table for string part in the parts. So for each string that's in the parts, we'll split it on the comma. So now we have bucket 0 should be our first value as a string, bucket 1 should be our second value as a string. And we'll go ahead and we're going to say system.out.println temp at bucket 0 and temp at bucket 1 is equal to logic dot and first value is going to be integer dot %, of temp at bucket 0, and then integer.parseInt temp at bucket 1.
Missing a plus. Before and.
And I should be able to kick that down, I think. Can I? So I'll just put it on 2 lines. It'll allow you to do this because we're concatenating. So we're going to create a little string. This will be 0 and 0 is whatever and returns for 0 and 0. 0 and 1, blah, blah, blah. So let's see the truth table here for ands before we do the rest of them. So go back into test. We're going to call logic.displayTruths. This should just give us our ands truth table right now. So 0 and 0 is false, 0 and 1 is false, 1 and 0 is false, 1 and 1 is true. Let's put a little space there. So that's for our and truth table. Or truth table. Here we'll put a little couple carriage returns at the beginning of each one. That's the OR truth table. And the NAND, no, we got the XOR truth table. Then the NAND. Then the NOR. And the XOR. So here's our AND truth table. Already saw that. Here's our OR truth table. It's true under all circumstances unless they're both 0. Here's our OR XOR truth table. It is only in the situations where there's exactly 1, 1 is it true. All other circumstances it's false. NAND truth table is true except when it's 1 and 1. So under all circumstances except 1 and 1. NOR truth table is true under all circumstances, or is false under all circumstances other than 0 and 0. And XOR is true only when it's either 0 and 0 or 1 and 1. It's false otherwise. That look right? Okay, was that the whole homework assignment? Anything else you had to do in there? So everybody got that? I have to give you a homework assignment? Did you bring me a coffee? He bribed me with the coffee this morning. All right. So I just read this thing, print e-label, really funny, and I thought that it would be interesting, like put a folder out here that's just like, you know, Ebola tests and then put a date after it. Just have that sit on my desktop. All right. Chapter 4. We finished that one? Those are a time.
Yeah, we went through all of it.
Yeah, like a day.
We went through 2 in a day.
Yeah.
Okay. Well, so just kind of operating off of this real quick. We have our combinational logic. So if we only use 2 inputs, we can build our own combinational circuits now. For we have this is an and, this is an or, this is a not, this is a not. So don't we have all the tools necessary to have 2 inputs, having one go into an and, have one go into a not, which goes into the and, then having the output of that goes into an or from another guy. We could build this in code, couldn't we? With the tools we have right now. And then generate our own logic table based on those inputs. Okay, but realistically, truth tables are more just informational things, right? They kind of tell us what the possible outputs of a circuit are. Realistically, if we were building this circuit for use, we know it can only be fed 0s and 1s. So we don't care what all the outputs are, we just care what the outputs are for a specific set of inputs, right? So we could have something that takes in 3 inputs, A, B, and C. Let's just build this real quick. It'll only take a minute. So I'm going to say static Boolean combo int A, int B, int C. Okay, so this guy happens to take in 3 inputs. So A is going to feed into an and. B is going to feed into a not, which feeds into an and. Just close this. So that is, we have logic dot and A, logic dot not B. Okay, so that's going to be our and. So that's the A and not B both feeding into the and, which is going to feed into an or. Logic dot or this guy along with this guy. So the result of this and along with C goes into our or. Then we not that answer, and that's our result. And actually, given this, it tells us we probably should have written the not. In terms of Booleans instead of numbers. Did we do that? I don't remember how we wrote it or not. No, we wrote it in terms of numbers. So actually, let's just give ourselves a second version of not. Take advantage of the polymorphism. So we have 2 versions of not. One that takes in a Boolean, just returns the opposite of it. The other one that actually flips bits. So this particular one is going to take the result of our or, which is a and. These guys need to be numbers as well. No big deal. Huh?
Now you got yourself
No, I'll just do a map. Actually, we'll do so all these guys. So I just created a 2-bucket array of map. Bucket 0 is false. Bucket 1 is true. So now all of our guys here. The map's going to work backwards for us. It's going to make these things look really dumb, but whatever. So we're going to make all these guys return ints now. We'll just do it for and first. So this is going to be map at bucket 0 equal this guy. So if map at bucket 0 is equal to that guy, then we're going to return a 0, else a 1. So map at bucket 0 is a false. So if this guy's a false, and that's equal to this guy, so if false is false, then we're going to return a 0, otherwise return a 1. We can do this even cleaner. We don't even need map. Dump map. So we could just say, if this is true, return a 1, else return a 0. I'm going to steal that part of it. Int for or. If this is true, return a 1, else return a 0. Int for Zor.
Simplify that, couldn't you just have if A is equal to 1 and B is equal to 1, and that A is equal to 1, and then the XOR symbol?
The XOR symbol does.
If you have A is equal to 1, XOR B equal to 1.
Does it? It does it at bit. It's a bitwise operation.
Okay.
You want to do the caret.
Yeah.
Caret's bitwise.
Right.
So it won't do. Actually, in that particular case, it would work. But generally speaking, what he's talking about is this. We've seen ands and we've seen ors as our Boolean operators in Java. There also exists an and an or. These are the bitwise operations, which means that if you had, these would take in integers instead of Booleans, and would deal with them on a bit-to-bit basis. So a 1 and, so let's say it was 1, 0, 1. Okay, 1, 0, 1 and 1, 1, 1. So 1 and 1, 0 and 1, 1 and 1. It would do all those together to do an and bitwise for the entire number. The thing he's talking about is there's another one that we hardly ever use, which is the caret. A lot of people want to use the caret to take something to a power in Java. It doesn't work that way. The caret is the bitwise Zor, XOR, exclusive OR. All right, so for this one, we have that whole thing. That. NAND, also have it return an int. Yeah. So for the logic and, NAND will be get the logic and if that guy is,
Well, that's going to return int.
yeah, if that guy's equal to 1, return a 0, else return a 1. Logic or if this guy is equal, this guy's equal to a 1, return a 0, else return a 1. Equal to a 1, return a 0, else return a 1. All right. Doesn't it like here? Whoop. Oh, I haven't changed my return type of this guy yet. There we go. All right, so now I can have my combo taking an int A, int B, int C. We'll pass in the A, the B, and the C in here. What's it not happy about here? Oh. Not, we do have two versions of not, correct? One that returns 0, 1. Okay, good. All right, now, this is the circuit that we see on that page. So if we pass it 0, 0, 0, our final output should be a 1. So logic dot combo 0, 0, 0. We'll print that out. Hopefully we'll get a 1. There's our 1. So 0, 0, 1 is going to give us another output, blah, blah, blah. Is this the same function? Yeah, this is a truth table for it. So 0, 0, 0, 1, 0 should give us a 0. Let's just test that real quick. 0, 1, 0. Is that the same truth table? Oh, no, it's not. This is just a not of B. Different truth table. Yeah, those are unrelated. I think ours works. Okay. So we have some neat code now after changing the return type several times. But whatever return types you used is fine. We just had to make ours more compatible to be able to build circuits like this. So now we're able to build our own combination circuits using ands and ors and nots and all that crap. All right, so this was chapter 4. Now let's look at chapter 5. Trucking right along. Okay, so we just started last time talking about Boolean expressions. And what we're looking at now is kind of taking this idea of what we've been dealing with in programming with a Boolean expression, any expression that boils down to a single value of true or false, and turning it into our problem-solving method for making hardware. Okay, so at some point, somebody's been writing these circuits, creating these circuits, and they're going to do them on paper or using, various computer software that allows you to build things with circuits, or the software that we just wrote that allows us to build things with circuits. to ultimately have inputs flow into a system giving us the desired outputs. All right. So the answer we have two different ways of representing a Boolean expression. We could do it through a picture like this, or we can do it through a truth table like this. And if we look at these two, this one at a glance maybe feels from a human perspective more meaningful because we kind of see the pieces that go together, like, oh, I could build this. And we just did it, right? We just used our program to build it. So what am I going to need? Well, I'm going to need, what's this guy? What kind of gate is this? It's an AND gate. What kind of gate is this guy? In fact, we actually just literally built this exact same one, didn't we? So we can, this is the truth table for the guy we just built, isn't it?
No.
Oh, we had a knot right here, didn't we? Okay, well, close to the same one. But in any case, knowing what pieces we have to grab from the toolbox, we could build this. Grab an AND, grab an OR, grab a NOT, an inverter. And with 3 inputs, we can hook these guys up, solder some wires together. Or if we don't want to solder, we can use a solderless breadboard that just lets you stick wires into it. And we might look at those the very last week of class. I have a toolbox somewhere here, probably in the room. It used to be in a cabinet that used to live here. But we'll bring some of those out just to show you what they look like. But we can certainly build this. And if we feed the right inputs, we'll get the output. Usually when we're testing this, you put a little light bulb here at the end. If it's on, that means it was a 1. If it's off, that means it was a 0, whether the light's on or not. Okay, when you're testing this stuff. So this is meaningful to us from a perspective of building it, schematic. This guy is meaningful to us just from an output perspective. Could you, if I just gave you this, truth table, could you build this? Short answer is yes, but not very easily. I mean, you'd have to kind of mess around with it. Could you possibly come up with a circuit that's different than this one that has the same truth table? Certainly, absolutely. So given this information does not give us enough data to build this exact circuit. Okay, so neither of these are really, adequate. So both schematic and truth tables take too much space. Can't really describe stuff very well. We like this one from a space saving better than this one, but certainly we can see this getting out of hand. Truth table hides the circuit information, so we can derive multiple circuits from one truth table. You might not get the most efficient version, but we even mentioned that last class dealing with companies when they're building their prototypes. They actually have a collection of either XOR or NAND gates. These are our universal gates. So they have a collection of those guys that can, between those and inverters, they can build any of the other gates. Allows them to buy in bulk and prototype stuff. So realistically, when they're initially prototyping these, they likely will not build the most space-saving circuit. They'll build the equivalent logic circuit, and once they tested it and know it works, then they'll have the circuit printer print it out. Okay? Okay, so schematic diagram is difficult to use when trying to determine output values for each input combination. So if we're just looking at this and I say, okay, you have 3 seconds. If I give it a 0, 1, and a 0, what's the output? You have to kind of mentally feed it through there, right? Until you get your output. But if I gave you 0, 1, and 0, you know it's a 1, looking at this guy. So they both have their benefits, but either one of them individually really isn't beneficial. So overcome these problems. Discipline, much like algebra, is practice that uses expressions to describe digital circuitry. These expressions, which are called Boolean expressions, use the input variable names, A, B, C, etc., and combine them using symbols. So for instance, and we talked about these a little bit last time, a 0, period, 0, that's an AND. So this is the Boolean expression for 0 and 0. 0 and 1, 1 and 0, 1 and 1. Okay? The OR, these aren't the ORs yet. They're just doing math. Okay, so Mathematical addition has similar parallel to Boolean algebra, though it's not quite as flawless. Whatever, blah blah blah. This is really
I really didn't know what
this is a meaningless thing. That's true. Okay, so plus is used for the or. So A or B, that's what this guy is showing for the Boolean expression. The not, we put the little hyphen above the A. So not A. This is not A and B, so this is a NAND. This is exclusive OR. So this is A XOR B, which is equal to not A and B plus, or not A and B, or A and not B. And so we can look at it this way, or we can think about it this way. These are equivalent. Okay, Boolean expressions of combinational logic, so it's similar to what we had at the very top. If we had this guy, what's the Boolean expression associated with this guy? So this is A period. Let's kind of write this out. Ooh, how do I do, I'm going to represent a period. Whatever. Huh? That's a good call. So A and not B. And we're going to put that together with an OR with C. And I'll move the not over. And then we're going to not that entire thing, which makes my picture very difficult, I think. Good enough. So something along those lines. So they started going through replacing aspects of this. We get down to something like this. So A and not B or C. That's what's out over here. But we need to have not. So not A and not B is not equal to not A and B. These guys are not the same. Don't have the same outputs. Then they showed you an example of that, unimportant for what we're doing. They don't actually ever show us our final answer, but what we have is fine.
Don't they?
Actually, they do right here.
Yeah.
Yeah. This is what we wrote. All right, so order of operation thing. To begin with, and takes precedence over an or unless overridden by parentheses. Not is a special case in that it acts like a set of parentheses. If the bar indicating the not function spans a single variable, it takes precedence over an and an or. If, however, the not bar spans an expression, the expression beneath the bar must be evaluated before the not is taken. So they're showing these guys are not the same. So if we have A and B, so let's say this is 0 and 0, not 0 is 1. Not 0 is 1, 1 and 1 is 1. So 0 and 0 is 0, not that is 1. For those examples, it was the same. So let's go 0 and 1. So 0 and 1 is, so not 0 is 1, not 1 is 0, 1 and 0 is 0. So now we have 0 and 1 is 0, not that is 1. So right off the bat, we have one where they don't match. So if A is 0 and B is 1, this side is not the same as this side. This comes out to a 0, this comes out to a 1. They're not equivalents. Okay? Well, these are just giving us math laws. It's fine. So commutative law, A or B is the same thing as B or A. A and B is the same thing as B and A. Makes sense. Associative law, A or B or C is equal to A or B or C. Similarly, A and B and C is equal to A and B and C. This is convenience if they're right next to each other. Obviously, parentheses play a bigger role, right? Most of us, we're not going to think about things in terms of cumulative or commutative or associative laws. We just kind of know how it works because we have so much practice dealing with parentheses, stuff like that. Distributed law, we can take A and B or C and turn it into A and B or A and C. So we can kind of multiply through if that makes sense. Relatively unimportant for us. Not A is A. So probably don't want to send something through two inverters unless there's a bunch of crap in between. Doesn't make a whole lot of sense. Let's see, I just want to skip through most of this. This is garbage. Here's some memorization rules for exclusive ORs. A exclusive OR 0 is whatever A is. A exclusive OR 1 is whatever not A is. A exclusive OR A is always 0. That kind of stuff. Stuff that we could solve on our own. Okay, and then certainly we can simplify everything if we wanted to, but like I said before, if you're actually creating these circuits at a hardware level where you're building this crap for industry or something, you're probably going to not simplify them at the time of prototype. You're going to simplify them at the time that you actually go and print the circuit. Okay, so if we think about the process of that, we're going to build a prototype and test it for accuracy. So you might have, you know, a bunch of wires sitting there with all these things connected together and have a part that works. Okay, this is not what we're going to sell on the shelves, but logically it's equivalent to what we're going to sell on the shelves. At that point, we have something we know that works. So then we write the Boolean expression that represents that combinational logic. From there, we can simplify that Boolean expression down to an equivalent Boolean expression that will probably, hopefully, take less parts that we're then going to print onto the circuit board. That makes sense? Okay, so it's kind of the process by which this stuff is built. And this is really more of a this is a newer thing, this idea of very large scale integration, VLSI. Historically, and this is why our components keep getting smaller and smaller and smaller. We go back to the early days of computers when a computer took up an entire gymnasium. Well, that's not just because transistors didn't exist. It's because behind all that stuff, we actually had the actual wires that hooked all that crap together. Okay, today we have a little breadboard, you know, kind of a little square thing that has a bunch of holes in it that power flows through, so you can plug wires into it and power different components and things like that you can go and buy at Radio Shack if you want. But if you're going to do that, go order offline. It'll be a lot less expensive. But in any case, we put all those things together, and that's our prototype. From there, we can actually then hire a digital printing company to print out a circuit board for us that has the equivalent logic. You know, those things exist. So for those of you who want to prototype things, if you go out and you get one of these Raspberry Pis or an Arduino, Arduino is simpler programming because you have to use their own programming language, which is a functional language built into it. A Raspberry Pi actually runs an operating system. So you are utilizing a full-fledged version of Linux, let's say, and writing software in a language of your choice. Could be Python, could be C, could be C++. I think also Java works with their API. And you can actually get the inputs from the stuff that's plugged into your Raspberry Pi. The Raspberry Pi is going to, just to show you what that looks like. Let's just refresh this real quick. Oh! Somebody get it.
Delivered 30 minutes ago. Over 30 minutes ago. 26.
Hold on. Everybody relax. Oh, no, we're still going. I'm going to have... We're still going.
Can I have Steve pick it up?
It's here. Go get it. I'm actually going to send that to a couple of different students. Hopefully one of them returns with it.
One of them's going to show up there and be like, it's not here. Where'd it go?
It's like one of them just takes and walks away with it.
eBay.
All right. The bad thing is I'm not going to work out now today. I was supposed to work out after class today, but this is more.
Just going to play well.
No, actually, maybe I'll get it set up in there patching and then go work out. What was it? Oh, Raspberry. Well, let me show you an Arduino first. So here's an example of an Arduino, and I have a bunch of these in a toolbox next door. So this is through a USB port. You plug this into your computer, and they have a piece of software that allows you to program it. So on this is a chip. It's a programmable chip that you can write to. Okay, and once you've written to it, you can unplug it from your computer. Now it's stored on there in firmware, okay, in ROM, and so at that point, you can. This is your breadboard thing, so you can plug, lights and crap like that into this. The thing also has a light built in. Where's the light on here? I think it's right here. It does have an LED built into it. It's somewhere, I think we just don't see it. It's somewhere like here. But in any case, you can build your own circuits off there. But what most people do is they run wires off of this. Each of these wires holds a different voltage. We have digital and we have analog wires, analog outputs coming off of this. So you might have a wire going from here over to a breadboard, powering that breadboard, and then you can have your circuits on that breadboard to do your different stuff. So you would build out your prototype. And just to show you a breadboard.
I don't think you're gonna.
Breadboard looks kind of like this. Okay? And they actually make breadboards for the Arduino. Did I just close that?
Yeah, you did.
Perfect. That are kind of the same size as the Arduino. And what you could actually do is you can mount it on top. This wouldn't be an example of it, but they have ones that actually fit right on top of the Arduino, so you can kind of build your entire prototype in a single setting. Here's kind of an example of what I was talking about. This isn't the mountable one, but this is them hooking the Arduino up to a breadboard, making outputs. Okay, so this would be kind of the intermediate thing. So if you are somebody who wants to build some sort of digital logic but don't want to have to deal with a lot of soldering, a programmable logic board like this allows you to write things in terms of Boolean expressions for most of the stuff. Let the Arduino do the work, and then the outputs light up LEDs and stuff like that. Actually show the output of your program. A Raspberry Pi.
Sounds really good right now.
Actually, I don't think it's just PI.
Go back to the other one. Look at the pictures. It's delicious.
Okay, a Raspberry Pi looks very similar, but these guys actually usually have SD slots on them, and at the very least have Ethernet and stuff like that to remote into it. But these run, let This is actually an older version. Doesn't matter. I can explain it here anyways. So these are kind of the next step up, where they aren't just running this very simplified interpreter for the programming language that comes with it. Instead, it's running an operating system that you load on there. I think by default it's running a very minimal version of Linux. I think it might be Minix, which is a very old one, but don't quote me on that. But they have special versions of like Ubuntu that will run off an SD card for Raspberry Pi, which really gives you a lot of flexibility on the type of software you could put on there. So this would be kind of the next level. I have a buddy who retired from Western Illinois University, but he still lives in Macomb, Illinois. But he, has his pension there, but he's not that old, so he works up in Chicago and he commutes, like twice a week or something like that. So he has his house in Macomb, Illinois, where he has fish. Wants to feed his fish. Well, you can go into Amazon and buy a fish feeder. That's not what geeks do. So what he did is he 3D printed this little wheel that he can then put the fish food in, and then he wrote an Arduino program that along with, he has some gears and a motor and stuff like that, on a period of time, it just turns the wheel, puts food into the fish water. So I think it'll run for like 2 weeks by itself just from this program.
So zombie apocalypse happens.
Right.
Fish is going to survive.
Right. And then he also has an example of, this was the last time I went in and visited him, he had an example of the ultimate offsite storage. Something happened with his Raspberry Pi and he didn't have his code backed up. Could have written it again, but I guess there was a lot of twerking he had to do related to, I'm not sure how that had to do with it, but he claimed it. So he had to do a lot of tweaking to the code to get it working. Well, his son is a missionary in Africa, and his son goes up to the mountaintop to call like once every 2 weeks. And I think the language he wrote it in was Python, which is a scripting language. The next time his son called, he said, well, his son had been interested in learning Python, so dad had sent him a printout of the code. So he had his son reading him the code back line by candlelight from a mountaintop in Africa. Kind of a interesting backstory. Okay, but in any case, these are kind of our modern way of our modern computer science people to create hardware stuff. We've kind of moved away from hardware. If we would have gone back to computer science 20 years ago, you would have been building circuits and stuff. I think when I was an undergrad, I built a programmable elevator. So we, built the frame out of wood and stuff like that. We had the elevator going up and down, stopping at multiple floors, and we kind of don't do that stuff anymore. Part of it's because our software has gotten so good that we're able to simulate those things, right? We didn't have iPhone apps and graphical user interfaces back then to mimic the elevator going up and down. We had to build the stupid elevator to make it go up and down. So in some ways more interesting, but in other ways time has kind of passed us by, and for some of these things. Now the two worlds are really separate. Some schools have a computer engineering school where you do all the programming stuff, but your main focus, we're out at 225, correct? That was it. Gimme.
Yeah.
Who brought it?
I think somebody from the mailroom. Is that the mailroom?
Go get it. Run back there.
You bring it here.
Bring
Yep.
it down.
Was he kind of tall, red hair?
Maybe. He had an iMac box in his hand.
That's kind of cool.
Bring me my iMac. So, in any case, in those engineering schools, you learn the programming stuff, but then you're actually building these real circuits. And you usually are dealing with electrical classes too, electricity, because at some point you're plugging this crap into on small scale batteries. On the, he just left. Okay, on small scale batteries. On a larger scale, actually plug in power into these things. So in any case, we've kind of moved away from that. So these new products, these programmable circuit boards have kind of come into existence to bridge that gap, and things have gotten geeky again. I think for a long time, people were not really building circuits. They were just buying things. But now there's a whole big market surrounding the Raspberry Pis and the Arduinos where we can now take an Arduino or a Raspberry Pi, hook it into an LCD output, and actually have something that does something interesting. I built something for my country club this last year that I'm looking for a waterproof housing for. When you go up to the par 3s, par 3 golf courses, golf holes, every single day they move the tee boxes. So I have my little laser sight. I go up there to find out what today's distance is, because on a given day they've moved the position of the golf hole, the hole on the green, as well as the tee box, where how many yards within the tee box you are. So for a par 3, you're trying to get it as close to the flag in one shot as possible. So it's beneficial to know the exact distance that day. So I built for one of our 9s, you have two par 3s on a 9. I built 2 little things that they can program through a website. These things connect through a cellular network, pull down today's yardage. So when the guy goes out there, when he first sets it up, he can take a scope of the flag. Let's say today's yardage is 138 yards. Hits the website, programs it. The box then pulls it down from the web over the cellular connection. And now it's programmed for that. It displays on there 138 yards today. Now you could also have done that probably with a chalkboard, but not as cool is the punchline there.
It would have been cooler if you had something that could actually put in like the bottom of the hole and then calculate it from where you're shooting off.
You really could. You really could, because all the flags now on golf courses, even though it's kind of fallen out of favor for people using these devices, they have a prism at the top of the flag, because there's a couple different rangefinder types. The one I use is a laser, so I actually just scope it through there. I don't require this. But there's another one that has been around for a lot longer, that a lot of the golf courses switched over to this, and they put prisms on top of the flag, so you just hold the thing up, and it just shoots out a bunch of things and hits the prism, bounces back, and it just tells you the distance. So you don't have to have as accurate. With mine, you're like looking through binoculars, you just get the crosshairs on it, and it reads it. But I wouldn't think there'd be a big deal why you couldn't have just a constant thing where it just always reads from the flag. You might have to have it scan side to side until it hit the flag or something like that, hit off the prism, but still an interesting thing. Okay, let's just see where we're going with this real quick. Okay, so simplifying expressions, we kind of get what that is. Can probably do some of that. I don't want to spend time on that. So we'll come back next time. Somebody remind me, we'll start off on chapter 6 and hopefully build some stuff. All right, have a good Thanksgiving. If you're traveling, travel safe, and I'll see everybody when you get back.